Yeah, well, I have the answer now because I emailed her and said, you know, I'm never in Welch Basement, so from now on, you have to email me the punchlines. So she did, but I haven't read it yet, so I can't help you with
Do you know the answer?
I don't know the answer.
Google it.
Why was the star arrested?
Was it why or where?
I think it was why. Why did the star get arrested?
Why did the star get arrested?
Criminal? Delinquent?
Because it was a degenerate?
Maybe.
It would work. I don't know if that's the punchline, because not enough people would think it was funny.
Yeah.
Broke some sort of law?
Yeah, I don't know. Not seeing it. So I asked her if she'd ever done the, because I can't remember, the star walks into a bar, says I'm the brightest star in the sky. Yeah, so. Anyway.
Do we have an exam sometime?
Sometime we do.
Sometime?
Yeah.
Ooh,
When did I claim it was?
There's one supposedly next week and then one supposedly the week after. The next week.
Well, there would be the final. I would. Oh, you mean for both classes?
Yes,
Right.
yeah.
Right.
Astro is next week and E&M is the following week, according to the syllabi.
According to the syllabus. Okay. E&M I'm definitely going to stick to. What do you want to do with Astro? Yeah.
Whatever.
Yeah.
Just tell us.
Yeah, okay. I don't know. When would we do it if we did it next week? We could, but I do want, I have a homework assignment I gave for Friday, because I I can put that off till Monday of the next week.
So I have the exam Friday, homework due Monday.
Yeah, or the exam Thursday, homework due Monday or whatever. Doesn't really matter.
If we do the exam on Thursday, we're gonna do that thing again, we have 3 classes.
Only if we skipped class to have the exam.
Although I will say,
Like that.
this,
Is it really long?
the senior class is going to a Clippers game next Thursday night,
Mm.
and I was kind of hoping to go to that, but
Yeah.
it's not necessary.
Do it on Wednesday, it's just less time to prepare.
Put the exam off 2 weeks.
I mean, there's that too. We
Yeah.
could.
Oh, on Friday, if that works for you guys.
That's fine.
Yeah, assuming I don't have to go to Ann Arbor again, which I may not. Friday would be okay. Okay, so preliminarily Friday, but I'm not sure. It'll depend on what happens with the Ann Arbor situation.
Yeah.
Yeah, and I'll know better this weekend because I'm going this weekend. So
Okay.
that'll give us some assessment. Yeah, okay. So either the exam's on Friday and the homework isn't, or the exam's not on Friday and the homework is.
Deal.
Yeah, all right. I'll let you know as soon as I have it figured out. About an hour before the exam.
Put the
Sure,
study
I
guide
can
up
do
an
that.
hour before the exam.
Yeah, right. Spiral density wave theory. Good stuff, actually. Fun with mechanics. As in, this is gonna feel like mechanics again, because it kinda is. So we're gonna adopt cylindrical coordinates, and while on some level I should use the same symbols that are used in E&M, I'm not going to, because the notes are all based on the symbols used in the book, and if I try to switch, I'm gonna write the wrong symbols when I'm looking at my notes here. So in our coordinate system, for our purposes, cylindrical coordinates, we are going to call what in E&M we're referring to as S, we're going to call that capital R. But we will retain phi as the azimuthal angle. And then, of course, we have unit vectors. Here, the book says ER, E theta, E phi. I guess I will just use R hat, theta hat, phi hat. R hat, phi hat, z hat, I mean to say. So, that I will do. Or at least try to remember if I write this up. What's that? No, it's little r hat. So in other words, well, actually it should be, yeah, it should be as a matter of fact. Okay, what should I do? I could do that, yeah, I better do that, because again, I'm gonna mess something up. So yeah, that's big R hat. Yeah, big R hat. Because you can never have too many ways of writing the same things. So the position vector, which we will call little r, yeah, so I definitely better not call that little r hat. Little r, the position vector is capital R hat plus z hat. And what we're going to do for these purposes is we'll put the origin at the center of the galaxy, because any other choice would be stupid. I know that's harsh, but it's true. And we'll put the galactic disk in the XY plane. Double checking that we're recording. We are, as a matter of fact. And we're going to assume cylindrical symmetry. Now, the spiral density waves are a breaking of the cylindrical symmetry. They indicate an azimuthal dependence. But in other words, we're going to assume that those are a small perturbation, and so we'll assume that we can still use cylindrical symmetry based on the density waves themselves being a small perturbation, which isn't necessarily true, but this would be a way of studying how, for example, how the density waves might be set up from an initially azimuthal situation. So assume cylindrical symmetry. Or in other words, the gravitational potential energy is independent of phi. Gravitational PE is independent of that azimuthal angle phi. Or in other words, the gravitational potential energy of a mass over there, which we'll call U, the potential energy, not the mass, is only a function of R and Z. In general, it would be a function of R, phi and Z, but it's only a function of R and Z. So now let's look at the equation of motion for a star of mass m. That'll be mass times acceleration equals force. So m d squared position vector dt squared, m d squared r dt squared, will be the gravitational force on it as a function of r and z, because it doesn't depend on phi. But force is minus the gradient of the potential energy, so minus grad u. And the components of the gradient in cylindrical coordinates are du dr r hat, and just for completeness, 1 over r du d phi hat, and du d z hat. component of zero because of the cylindrical symmetry, since U doesn't depend on V.
Love it when things are equal to zero.
Yes.
I like when we make things equal to zero.
What?
So I like when we just make things equal to
Make things equal to zero, yep.
Like the divergence of the vector potential. Let's just call it zero.
Let's make it zero because we can. Yes,
I mean, it would be not necessarily helpful otherwise.
that's absolutely, well, yeah, that's true. There are times when you don't want it to be necessarily equal to zero, but we're not in those times. So,
Will we get in those times?
no, we won't, as a matter of fact. Defining the gravitational potential as opposed to being the potential energy. We've met this before when we talked about the binary star systems. Capital V is U divided by M. We obtain for our equation of motion d squared r dt squared is equal to minus d big phi dr r hat minus d big phi dz c hat. Now the notes claim that in problem 2513 you'll show the expression for the acceleration in cylindrical coordinates is blah, blah, blah. I ended up not assigning the problem because you had mechanics, and you probably did it in there, and if you didn't, pretend that you did so that I don't assign you the problem.
Yeah, we totally did.
Totally did that.
I'm not sure. I don't
No. But in any case, you certainly talked about how in different coordinate systems, it's not just d squared x dt squared, d squared y dt squared, it's more complicated in different coordinate systems. By doing problem 2513, you could show,
You could.
I didn't say would, you could show,
You could happily show.
very happily,
It felt weird without that adverb.
yeah, you're right, it is required. It's totally not right to not have it. That in cylindrical coordinates, d squared r dt squared is r double dot minus r phi dot squared for the r component plus 1 over r times d dt of r squared phi dot for the phi component plus z double dot z hat. So the z component's nice and easy, it's just z double dot, but the other ones are more complicated in cylindrical coordinates. So, two vectors are equal if and only if their components are equal. So we can say that the r component has to be minus d phi dr, the phi component has to be 0, the z component has to be minus d phi dz. So it must be that r double dot minus r phi dot squared is equal to minus d phi dr. That 1 over r ddt of r squared phi dot is equal to 0, because that's the phi component of the force. And z double dot is equal to minus d phi dz. equations of motion for our star mass F.
Why do we want the equations of motions in terms of the gravitational potential?
You'll see, that's what it comes down to. So, hang in there. This is a, just trust me, keep following along on the journey, and eventually you'll see the lovely scenery that comes over the hill and enjoy the vista.
Windows Vista.
Windows Vista. No, you don't enjoy the Windows Vista.
Windows Vista had nothing wrong with it.
Is it easier?
It wasn't terrible.
It was pretty. I'll give it that, I like the look of it.
Yeah, mine did. 7 was bad.
Windows, the only reason,
I like Windows 7.
I like Windows 7 a lot. The only reason Vista was so bad is because it was following up XP, and XP was perfect.
Well, it's that thing with Microsoft where it's like the release quality goes beep, 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 basically.
Oh, it looks like the density of atoms.
Yeah, right.
Based on their number.
But, in any case, Linux. So,
It's free, you can't argue with free.
now we want to look at the torque on the star because we're going to show that its angular momentum, in particular, the z component of the angular momentum is conserved, and that's going to be important to us. The torque on the star about the origin is tau equals r cross f So, in the usual way, we make our determinant of goodness. So, R has components R0Z. There's never a phi component to R because just the way the coordinate system is set up, right? In other words, for any cylindrical coordinates in general, R is R hat plus ZZ hat. No phi component ever because that would need to be tilted over. And meanwhile, F has components of F sub R, I'm writing all things. F sub R, 0, F sub Z, we'll write it as. Because before we showed that the phi component is 0, and then there's an F sub R and an F sub Z. And so, notice that the R component is 0, the Z component is 0, the phi component is not 0. So this is Z times FR minus R times FZ phi hat.
What is this F?
The force on the star. So we're just
Total
generically,
force,
right, we said, right, the force on the star, whatever it is, the point is it only has an R component and a Z component because of the azimuthal symmetry. du d phi is 0, and so there's no azimuthal component of the force. So in particular, tau sub R is equal to 0, but what we're really interested in is tau sub Z is equal to 0. The Z component of the torque is equal to 0. So that says L sub Z is constant, where L sub Z is the Z component of the orbital angular momentum. Since, of course, right, Newton's second law for torques is torque equals
IM. Or, it's like,
That version.
is that
That version.
that version? Yes,
The-
that version, right? As opposed to So if tau z is 0, LZ stays constant, in other words. Now, let's write down what LZ is. L, in general, is R cross MV, it's R cross P. Actually, it should be capital M because our star was capital M because it's mass. So R cross MV. So if we write out our determinant of goodness, R hat, V hat, Z hat, R, 0, Z, and then in cylindrical coordinates, the components of V are R dot in the R direction, R phi dot in the phi direction. Right, you need R d phi to get the little piece of displacement in the phi direction, since that's an angle. So MR phi dot in the phi direction, not just M phi dot. And then MZ dot in the Z direction. So the one we're interested in, L sub Z, is equal to what?
M R squared phi dot minus 0.
Right. So M R squared phi dot minus 0. Yep. M R squared phi dot. Notice that that's also M times the phi component of the velocity times R, because V sub phi is R dot. So this is MR dot times R phi dot. This is MR times R phi dot, and R phi dot is V sub phi. So this is also MV phi R. So mr squared phi dot is a constant of the motion because L sub z is constant. So mr squared phi dot is a constant of motion. So if r goes down, phi dot has to go up and vice versa. If it's not on a perfectly circular orbit, it's going to go faster when it's closer to the center. So now let's talk about the angular momentum per unit mass. This is a long journey, but it's a journey worth taking. Is J sub z, so L sub z divided by M. So that's just r squared phi dot.
We had that in E&M today too.
Current density.
I know, yep. It's just, well, you can never get tired of using the same symbol for different things. Never ever can you get tired of that. So phi dot is J sub z over r squared. And r phi dot squared is J sub z over r cubed.
So we're going to rewrite our equations of motion.
Yeah, we are, as a matter of fact. So thus, looking at the first equation we had before, r double dot is minus d big phi dr plus jz, let's see.
Wait,
No, this
how
has
did we
to,
get
yeah,
that?
that needs a
Okay,
square, sorry.
that's what I was
about
just
that.
about to ask.
Yeah, that needs a square on it, yeah. Whoopsie daisies, yes. Plus jz squared over r cubed. That's just a rewrite of our earlier result that r double dot, if we solved it, just minus d over r. solved it for r double dot, and then we just substituted for our phi dot squared is jz squared over r cubed. And it is convenient, as we will see, for us to do so, in particular because the angular momentum per unit mass is constant, since L sub z is constant.
And mass is constant.
And mass is constant, yes. Yeah, our star is not allowed to be shedding mass as it goes along.
We're gaining mass.
What's that?
We're gaining mass.
Or gaining it, that's right. It's not allowed to do either one. But notice that this is minus ddr of phi of rz plus jz squared over 2r squared. Right, because derivative of 1 over r squared is minus 2r to minus 3. And so we can write the right-hand side there as the derivative with respect to r of the quantity phi plus jz squared over 2r squared. So that means we should define that stuff in parentheses to be something. And that something is the effective gravitational potential. Ooh, yeah.
I bet that's gonna be in all caps.
You know what it's going to be. Yes, you're absolutely right about that.
You should
Amazing.
underline it instead.
No, don't do that.
No. Uh-oh.
I'm putting it in all caps.
And then put an overline over
Everybody's sort of happy. But
Nobody's happy.
I think
Actually
the
happy.
EH is the only happy one.
That's right. Yeah.
Just right potential.
No.
No.
I'm committed to this.
For some reason, it just makes me think of like a preschool.
Yeah, that should be, every letter's a different color. Effective gravitational potential energy.
You have a box of colors there.
Yeah, I do, as a matter of fact. Theft of R and Z.
I can't spell gravitational. Gravitoid?
Why did Sark get arrested? He got charged for theft.
There you go. Oh, boy. That's way better than whatever her punchline is. There's our effective gravitational potential. And in terms of theft, we got nice equations of motion. In terms of theft, we get to write that r double dot is minus d theft dr.
Is this another one that's actually pronounced Fef normally, or is this just you?
This is totally me.
Okay. That
Yes.
means we're gonna, everybody go out and pronounce it Fef
You
all
know
the
it,
time.
that's right. We're gonna fix the mispronunciation that's rampant throughout the field. And z double dot is minus d theft dz. If you're driving in a car and you think it's really great, that's Grand Theft Auto.
Wait, don't you have to steal it for it to be?
It's theft. It's not theft, it's theft. So no, not necessarily.
I don't get it.
All right, so here's the question we'd like to ask ourselves that will finally get us to this slide over here. For a given value of jz, for what values of r and z will theft be a minimum? back to that. We'll get back to that.
Be patient, Mark.
Yes, be patient, Mark.
Oh, it was missing.
You can't always have instant gratification.
I quit.
Infinite gratification.
For a given value of JZ, for what values of R and Z will Feth be a minimum? In other words,
But I'm confused. For a given value of JZ, for what values of JZ?
oh, sorry, that's totally wrong. Yeah, that would be confusing, wouldn't it? What values of R and Z will it be a minimum? Where's the point of the minimum is the question. In RZ space. In other words,
It sounds to me like we're gonna do some calculus.
yeah, we are. 2, 4, 6, 8. Time to differentiate.
That's great.
That's great. That's right. Where is dFFDR equals 0 and dFFDZ equal to 0? Where's that happen?
Somewhere.
Somewhere. Yes. Let's find out where in a minute. If also R dot is equal to 0 and Z dot is equal to 0, then the star will remain at this point in the RZ plane. Because if we look at our equations of motion, R double dot's minus dFFDR, Z double dot is minus dFFDZ. So if the star is at a place where these two things are 0, then R double dot is 0, Z double dot is 0. So if it ain't moving in the RZ plane, it stays there, right? This is like a particle that's at rest with no force on it. This is only in the RZ plane. It's still moving in phi, but it's not changing its R and Z values, is the idea here. So note that R and Z stay constant. But phi changes as the star orbits. The star is ultimately going around the galaxy. So phi changes as the star orbits. So what's this going to represent? If R and Z stay constant but phi is changing, what kind of motion should that be?
Uniform circular motion.
That should be circular motion, right? Uniform circular motion. And so let's show that in fact that is uniform circular motion. So by symmetry, the minimum must be in the midplane. It's not at some positive z or negative z. It must be at z equals 0 in the midplane. Z is equal to 0. So we have dFFDR, where we're going to evaluate the derivative at R for the minimum, comma 0. So we're using the fact that it's going to be at z equals 0. Well, that'll be given the definition of theft, that'll be d phi dr, d big phi dr, minus jz squared over r cubed, using the fact that theft is phi plus jz squared over 2r squared. When I take the derivative with respect to r, there, well, in general, right there, then we'll get minus d phi dr minus jz squared over r cubed. We want that to be equal to 0, because we want to be at this minimum. So r sub m are at the minimum.
Looks like it says rat minimum.
What? Rat minimum, that's right, yes.
I am a fan of rat minima.
Yeah, not a big fan of rat maximum.
Rat extrema.
Rat maxima, that sounds like an action movie.
It does, yeah.
No, it's rat extrema.
Rat
Okay,
extrema.
rat extrema.
Rat max.
That's why.
Yeah, well, that's where it's coming from.
Oh, wow.
So, the ordinary phi dr at this point r sub m 0 is equal to jz squared over rm cubed, right, just over there, jz squared over rm cubed. But jz squared is r sub m v sub phi squared over rm cubed. So this jz squared needs to be evaluated at rm 0. So we plug in the generic expression for jz was this rv phi, plug in r sub n. So that's v phi squared over rm. Okay. Yeah, it does, right? Yeah, I'm feeling centripetal here, or centripetal, I should say here. And thus,
Banished.
yeah, that's right. No, because I'm gonna be jumping into lots of rotating non-inertial frames, so I'm okay. And thus at rm comma 0, we have f sub r at rm comma 0, which is minus m d phi dr is equal to minus m d phi squared over r sub m, right? Because the force is minus m grad minus grad u is m phi, so minus m d phi dr, the force, the r component will be the r component of the gradient minus m d phi dr, is going to be minus m v phi squared over r. And so that is force equals mv squared over r. Whew. That would be uniform circular motion, the equation of uniform circular motion.
So does V not have any other components?
So if we're at the minimum, r and z are staying constant, and the only thing that's changing is phi. So in other words,
Oh, I see.
no, it doesn't have any other components. If this really is a circular orbit around the center, which is just the equation of motion for uniform circular motion.
That was a lot of work for something that we totally knew.
I know,
But it felt good.
but it felt good. Yes, that's right. So we certainly were hoping that's what.
Mark's not so sure.
It's just funny.
Maybe that's my problem.
It's nice to confirm our suspicions. But that wouldn't be very interesting, right? In other words, if all the stars were doing this, okay, everybody moves on a circular wall, right? So, in the disk. So no, that's not what we want. We want to look at what happens if it's not a circular orbit. What if we are close to a circular orbit, though? That's what we're interested in. Is what if you're not on a circular orbit, but you have a certain amount of angular momentum, and it's close to the right amount of angular momentum for that to be a circular orbit? What happens then?
Is that like Earth's orbit?
Yeah, like Earth has a Earth is an almost circular orbit. And so you can say that its angular momentum doesn't quite match up with the right value for it to be on a circular orbit at any given point of its orbit. I mean, you could certainly make a circular orbit that had the Earth's angular momentum, orbital angular momentum, but at any point in its orbit, that doesn't quite match what the angular momentum would be for a circular orbit at that radius, and so it doesn't stay on a circle. What if that's true for our star? So what happens if orbit is not quite circular? Well, what I like about this, and you can actually do this for the solar system too, you can do this for orbits around the sun, that's a homework problem. Remember epicycles and deference a la Ptolemy? To lowest order, you can consider a nearly circular ellipse to be a combination of an epicycle and a deferent. And that's actually what we're going to do here. We're going to show that to lowest order, the motion of the star is it moves on, it turns out not a circular epicycle for Keplerian orbits for 1 over r squared force, that actually the epicycle turns out to be circular. So in other words, Ptolemy's description actually turns out not to suck from some standpoint. But for, so the lowest order, the ellipse is just a circle with an epicycle, deferent with an epicycle. We're going to show that that's true for our stars in this more general potential, and the ellipse, the epicycle is not circular, it's ellipsoidal, but it's great. We're actually going to talk about epicycles here, and I find that very satisfying. What happens if the orbit is not quite circular? Well, of course, we want to do a perturbation analysis. So let's do everybody's favorite. Let's perform a Taylor series expansion about the minimum. R is equal to R sub m. Z is equal to 0. Writing rho, by definition, is the value of R minus the value it would be if you were at R sub m. So R minus Rm. So if you're not on a circular orbit in general, R isn't quite R equal to Rm for the given total, for the given angular momentum per unit mass, or just angular momentum for that matter, doesn't have to be per unit mass. We expect rho to be a small quantity. The star should oscillate in and out, a little bit bigger than R sub m sometimes, a little bit smaller than R sub m other times. So, Pfeff of RZ will be Pfeff at the minimum plus d Pfeff dr evaluated at the minimum times rho, R minus Rm.
Right, like
FDR, right, yes. Plus evaluated at the minimum times z, because it would be z minus 0, right? You know, z minus z naught, but z naught is 0 here. And we want to go beyond first order here because of the fact that we're expanding around a minimum, so these derivatives are 0 at the minimum. So we have to go to the second order terms. So there will be a contribution from the mixed partial. So d squared f dr dz times, evaluated to the minimum, times rho z, right? Generically it's d squared f dx dy delta x delta y. So here it's delta r is rho, delta z is z in this case, because it's z minus 0 and r minus rm.
It's rosy.
Rosy, it's rosy. Right. And then plus 1 over 2 factorial, also known as 1/2 d squared f dr squared times rho squared, in other words, plus 1/2 d squared f dz squared z squared plus, now we'll be satisfied, dot, 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 dot. How come there's not a 1/2 in front of this term?
I was about to ask that.
Because there's two of them and they're equal.
Because there's two of them and they're equal by equality of mixed partial. Right. Right. You'd have a 1/2 derivative with respect to z and r, 1/2 derivative with respect to r and z, they're equal, so you just combine them. So the two first derivatives are equal to 0 because we're expanding around the minimum. We're expanding around the equilibrium circular orbit. Furthermore, the z derivative of df dr evaluated to the minimum should also be 0 because df dr is going to be symmetric around the midplane. Since phi itself is. And we're assuming this symmetry, that it's symmetric around the midplane, that the potential is just a mirror image below the plane as it is above the plane. And so that means that df dr is going to be symmetric. Right, so here, as a function of z df, I'm just making this up, df dr might look something like that. It needs to be symmetric around the midplane. So in other words, the derivative with respect to z of it will be 0. The line would be tangent to it. Wow, get over it.
That's an awful noise.
What's that?
Awful noise.
Yeah, I know, it's really irritating, isn't it? So I'm going to steal a couple minutes because we started a couple minutes late. So I'm going to steal a couple minutes, so to speak, right? So,
Sounds like that.
yeah, that's right.
Grand theft.
Grand theft, yes. And I'm doing it automatically, so it's grand theft auto. There, I made it work. All right.
Miss this. Only slightly.
Thus, phi of r z is approximately phi at the minimum plus, we'll call it 1/2 kappa squared rho squared plus 1/2 nu squared why we're just saying that we will define the second derivatives to be,
Kappa, right?
kappa,
No,
rho.
kappa
Yeah,
nu.
kappa and nu, yeah. So kappa squared is the second derivative with respect to r, and nu squared the second derivative with respect to z. So we're gonna say that's kappa squared, and we're gonna say that's nu squared. Because, you know, they look like spring constants, right? This is that usual idea of if you're near a minimum, you get simple harmonic motion. That's the whole idea here. Unless the second derivatives go away, a minimum always looks like a parabola, a paraboloid, I should say. So this is a two-dimensional harmonic oscillator potential. Of course, we all know how to write harmonic.
Oscillating up and down
Yes,
these letters.
indeed. So this makes at least me very happy.
It's like an effective happiness.
Yeah. Thus, rho double dot, which is minus dphi dr, evaluated at the minimum, so that's approximately minus kappa squared rho. In other words, our equations were r double dot was minus dphi dr, but r double dot is rho double dot because rho double dot is r double dot minus rm double dot, but rm is a fixed minimum point, so that's 0. So rho double dot is r double dot. Z double dot is minus dphi dz. We're expanding around the minimum, so it's a second order. That's minus nu squared z. Simple harmonic motion, right? With frequencies given by kappa and nu. Angular frequencies given by kappa and nu.
How are you getting this kappa squared rho? Or,
Oh, because of the fact that, let's see, because of, yeah, so this is, let me think, it was obvious when I wrote it down, I didn't even think about it. Right, so, because we're taking the derivative of f with respect to, r, but that's the, yeah, actually, so let me look at it this way. It's the derivative, you could do this just as well. You could make this the derivative of f with respect to rho. Yeah, is what I wanted to do here, because differentiating with respect, so, yeah, so here's it. R double dot is minus dphi dr, right? Here is phi as a function of r and z, okay? And furthermore,
oh, I see.
yeah, what I really was getting at before is dd rho is ddr because of the fact that rho and r just have a constant difference between them. So therefore, when I find minus dphi d rho, this is a constant term, and kappa is a constant, nu is a constant, they're just those derivatives, right? So actually, I should probably like, take these off. It's really, I'm just taking the derivative of phi in my approximation here. And so I'm taking the derivative with respect to rho of 1/2 kappa squared rho squared,
Yeah. I see.
which is minus kappa rho when I put the minus sign in front of it. So that's where it comes from. So rho double dot is minus kappa squared rho. Z double dot similarly is minus nu squared z because I'm taking the derivative with respect to z of 1/2 nu squared z squared. Yeah, so thanks for asking the question because that made me explain it correctly. Yes. So, happy now? Okay. So, some harmonic motion in two directions with two different frequencies.
Nothing you haven't seen before.
Nothing you haven't seen before, right? And so, this is an illustration of the idea of what's going on. Essentially, it's take a marble, right? Put it in a parabola, in a bowl-shaped depression, and let it move around. And it's time to go, but we'll talk about then next time. A consideration is if the frequencies are commensurate with one another, if an integer times nu is another integer times kappa, you'll get closed curves. But if they're not commensurate, you get curves that don't close on themselves. Have you guys ever done Lissajous figures before? Like on an oscilloscope?
Yeah.
Right?
Wait,
Not on an oscilloscope, but I've
Right. Let's play a little, we'll close out with this little video. Mallory watched the video of Lissajous figures explanation. So what we're going to show here is an oscillation in the x direction and an oscillation in the y direction. If the frequencies are such that an integer times the x frequency is another integer times the y frequency, that means that after a certain number of periods in x, you'll have also gone a certain number of periods in y, so you'll be back to the point that you started at. So in other words, you'll trace out, if you plot x and y versus time, you'll trace out a closed curve because you keep coming back to where you started, as long as, say, n cycles in x is m cycles in y, then after the time corresponding to n cycles in x and m cycles in y, you'll be back to the same point. And since they're both sinusoids, you'll keep repeating the motion. So you'll trace out a closed curve as a result of that. You can do it on an oscilloscope by driving the x input and the y input with sinusoidal signals with commensurate frequencies, and then on the oscilloscope it'll trace out these so-called Lissajous patterns. And if you don't have them commensurate with one another, the pattern never closes on itself. So this is entertaining to watch this.
Lissajous sounds French.
It must be, yeah. So here's where the x and y frequencies are equal. That's
Whoa.
Uniform circular motion.
Oh, I've made
right?
those.
Have you?
On Mathematica.
On Mathematica, yeah, right. So here's a bunch of different examples.
Oh, that's crazy.
Mm-hmm.
I have a notebook that I made a bunch of these.
These are fun. Pretzel. I like this one.
Yeah, that's cool. I have a manipulate notebook where you can change the coefficients of.
Oh yeah, you can do that.
images.
Absolutely, you can do that. Yeah.
Yeah.
Right. Yep.
I didn't know this was these were called.
Yeah.
Yeah, see, I like the ones that look like that.
Right.
Yeah. Look like pillow designs or something.
Right. So in the RZ plane, our star can execute a closed pattern if the frequencies are commensurate, and it won't execute a closed pattern if they're not commensurate with one another. Kind of a little fun fact there. And is this what goes forever? Is it looping? No. Okay, it's about. I guess they just decided you want to see it more than once. Cool. Yep. Good way to end the meeting. I think where your education better than my education was, because I never saw the explanation of spiral density waves as an undergraduate, and I also never saw it as a graduate student either. It was only when I started teaching this course that I saw this explanation of where spiral waves come from. So you guys get it. It's like,